Okay.
Thank you.
So our next speaker is John Martinis, and he will tell us about quantum error correction with superconducting qubits.
Thank you very much. I really enjoyed the last talk yesterday where we were discussing about what the definition is of fault-tolerant quantum computation. And I thought it was really interesting because kind of the way people were talking about that there was really different than the way we think about it as Google. It's as if we were living in parallel universes. And it kind of reminds you of like Clinton and Trump supporters talking politics. It's really weird. So I'm not going to say that I'm going to resolve this. I think it's an interesting problem. But what I want to do is give you a description of how we look at the problem. And it's kind of different starting point. And what happens is I think the idea of fault tolerance actually falls out of a discussion of something I will call bigly quantum error correction, okay? Where we want to do quantum error correction at a very high level to good enough to make a quantum computer. Okay, let's start with that assumption. That's what we want to build. And then we talk about, okay, how is everything going to fall out of that? Okay? And I think for us, it's a very natural way to talk about the problem. Whether it'll resolve all this, I don't know, but we can at least move on. So what's the strategy? Okay, we want to build real quantum computers with error correction. And what does that mean? That means we have to base this on our algorithm size, which is going to be, let's say, 10 to the 10 or 10 to the 15 operations, kind of like conventional algorithms. You need that many gate operations. Okay, and based on that, you're going to need to build qubits with logical errors, say 10 to the minus 10, really, really tiny. Not zero, but it's tiny, okay? And of course, on top of that, you're going to have to build logical gates, okay? But let's just think about mostly the errors for that, because that's hard enough. Now, how are you going to get to a 10 to the minus 10 logical gate? Because the qubits themselves have very modest amount of coherence. They're analog, and we have to build this big digital system. So the way you have to do that I think, barring some new discoveries, okay, is that we're going to need to have some error scaling, and we're going to have to do multi-order correction. So you're going to have to correct it to first order, and then correct to second order errors, and third order, and fourth order, and fifth order, lots of orders, so that the logical error rate can be this small, okay? This lambda here, somehow this got erased from my computer. This is basically the error rate divided by the threshold. Okay, so you need low error rates for lambda to be big in order for you have to do this. So the visual illustration I have here is I'm standing here with my physical error rates, and way over there I have 10 to the minus 10 errors. And I do first order, and then second, and then third, and fourth, and fifth, and sixth, all the way over here to do 10th order. And then someone's going to say you need 15th order, so I ask Google for more money, and then I start trudging out here to do higher and higher orders. Okay? And of course, the larger the steps I get, the bigger the lambda, the better it's going to be, because I don't have to ask for so much money. That's great. Okay, now, let me tell you what's really kind of weird about this. Right now, we have zero error correction. And if I were to do from 0 to first order error correction, to go backwards, where there's more errors, but then once I start with the first order, I go to second order, and third, and fourth, and fifth, and sixth, all the way out here to 10th order or 12th order. The fact that I went backward a little bit, way back there, going from no correction to first order correction, I don't care, right? I have to go to so many orders. The fact that what's going on between no error correction and one error correction, okay, it matters, but not that much. So then why are we defining fault tolerance by what you do in first order correction, okay? I don't understand that. Okay, so maybe people can explain to me afterwards. I understand there's some interesting reasons why to do that, but if I take a step and go a little bit ahead, or take a step and go a little bit behind, I don't really care because I'm looking out there, okay? So the real thing about doing, good quantum error correction to build something is whether we have a good lambda, okay? And whether we have a good lambda, and whether we can make lots of lambdas, lots of steps, okay? That's what we care about. So God, I wish this thing would display my thing. Okay, well, I'm just going to have to live with that. So what we're going to do is we have to worry about lambda. How do we make our qubits big enough? And what we're going to talk about here is, how are we going to do that? So we want to be, of course, forward compatible to logic gates, but we're going to use the surface code, okay? And what we're trying to do right now is to try to make eventually about 1,000 qubits. And it's 1,000 qubits aren't going to take us out there, maybe around here. But this is far enough to know what's going on here. Okay, and then we can ask for more money or whatever to go farther. So let's do that. So, okay, and then we're trying to build up a lot of qubits, okay, by we're trying to build up a lot of qubits in a way that's scalable to maybe 1,000, okay? But also in a way that we're not going to have various correlated errors, which is going to cut off our march at some point. So you have to worry about that. So we're doing that. Now, getting to way out there, okay, that's going to be some time in the future. What we're trying to do right now is to build a system of 49 qubits, so that we can test whether we go forward or backward, we don't care, but we want to make sure that we can do a step forward and we have a lambda greater than 1, okay? And the only way to know that, to know whether we're going in the right direction, is to compare first order to second order. Comparing 0th order to first order tells you something, but it doesn't really tell you about this lambda factor and whether you're going in the right direction. So that's what we're trying to do, is figure out how we're gonna measure that lambda. And that's gonna require to do that. So that's 1,000 qubits, we're gonna need about 49, okay? And the reason we feel a little bit confident that we can do that is we did a bit flip error correction on 9 qubits. And it was successful and we knew how to do it. So we already have experience in this. But of course, building 49 qubits is some work, but that's what we have to do, okay? Now let me make one more point here. This whole concept of what is the step and what is lambda, okay? You might think that that's really complicated, okay? You're gonna have to measure this and do all these things. No, it's very simple. You just measure the logical error rate for n equal 2, and the logical error rate for n equal 1, and you divide those two, and that directly measures lambda. So although we think we know how to predict how far we're going, okay, we can actually measure that. And then we can see if it makes sense and it's going. So you absolutely will know that you're making some progress over there. You don't know how far you can go, you just have to do it. But you can reasonably guess that if you make several steps, you're going to keep going, and it'll be okay. So in terms of system performance then, given that the layer goes as lambda to minus n, I mean, you're going to expect that somehow errors matter, and somehow the number of qubits matter, because that's what we're doing. And then if you look at like newspaper articles, I get requests for interviews all the time. They're always talking about, okay, how many qubits do you have, blah, blah, blah. It's not a one-dimensional horse race. It's a two-dimensional horse race to do this. You have to have low qubit errors, and you have to make lots of qubits. Okay, lots. Okay, and okay, we're down here, and we have to learn how to do that, and it's fine. And of course, the threshold for surface code we want to do is around 10 to minus 2. And I'm going to note this axis right here. It's very tempting for physicists to tell you their best qubit numbers. like single qubit errors. But you know, we're building an engineered system. It's the worst ones that always dominate you. So this is typically your 2 qubit errors. So here we are, we have 9 qubits and a little bit better than 1% errors. We need to get down here to about 10 to minus 3, 50 qubit device. And you know, once we kind of hit this, or maybe a little bit more, then we can think about scaling, okay? And like I said, this is not really what you want to measure. In fact, you want to measure lambda, which is your kind of error correcting gain. So that if the lambda is less than 1, over here, you're in the death region, where if you make your integrated circuit better, it doesn't do you any good. It's like building an integrated circuit amplifier with transistors with gain less than 1. Okay, no one's going to buy that. It's not very useful. But as soon as you get lambda greater than 1, it starts getting useful. And in this region, it's kind of like the better the qubit lambda, the smaller the number of qubits you get to get. And then that kind of happens here. At some point, you only get logarithmic improvements. So it's better. But you really want to try to improve this as much as you can. But you know, to a reasonable number is all you need to get the gain to work. OK, so that's what we're trying to do. And we're going to be talking about, you know, moving to here. We're not quite there yet, but we want to move in that direction. Now, we want to measure lambda with quantum error correction. And I'm really not going to talk about how to do that. You can go back to our old bit flip paper and see how we did it there. But I want to talk about how the fact that we want to be able to predict how far we're going to step in this direction. Okay, so how are we going to predict that? Okay, clearly you can measure T1 and T2 and do some estimates from that. You can do some tomography, which is a number of operations, say 1, a couple qubits to see how it's going and make sure things are working right. But the kind of workhorse way to do that for us seems to be randomized benchmarking, which is for 1 qubits, for the number of qubits, we do a lot of depth to it, and a lot of number of operations. Make sure that we can run operation after operation, and everything's going to be OK and make sense. So we do that. We can do that for 2 qubits. And then what we're going to do is, since we're using 1 and 2 qubit gates, we kind of add up all the probabilities of those errors to say whether your error correction code, which has a large number of qubits and a large number of operations, are going to work, okay? And you want to know whether you can just add up the probabilities, which is not at all obvious for a quantum system. And what I would say so far, when we compare those error probabilities, the experiments experiments we've done can kind of be predicted by randomized benchmarking to about a factor of 2. And my guess better, we just haven't done all the measurements careful enough to put a bound on that yet. And it's great. We can compare the measured lambda with error correction with randomized benchmarking. OK, that's great. So now what I want to do is go on with this kind of the rest of the talk. I'm going to change gears here and say, let's think about this comparison, because this is a big leap here. 1 or 2 qubits all the way to 50 qubits, 100 qubits, lots of qubits, big leap. Yeah, do you really want to do it? Isn't there something intermediate we can do? And there are some ideas to do randomized benchmarking in the intermediate regime. That's interesting. But I'm going to introduce something which I'll talk about the rest of the talk, which I'll call quantum supremacy benchmarking. And we'll talk about why I'm doing that, which can have a modest number of qubits and a non-modest depth, kind of the same area this, but it's now with number of qubits. And it's going to be a way to measure the fidelity of what's going on with a complex system so that we can kind of go in between here and make sure things are going OK. And of course, we're going to have to do error correction in the end, but at least it's going to tell us if things are going wrong, and it's just another tool that we can do. OK, so what does that mean? What's going on with this quantum supremacy? Why are we doing it? It sounds like kind of a diversion, and a lot of people have commented on this. I'm going to call it as this beautiful road with wonderful vistas and a great view. It's wonderful. So that's why we're doing this. It's kind of a cool idea. And the cool idea is that when we want to build a quantum computer, and why we're getting a lot of money put into this field, billions of dollars, It's all based on the assumption that you kind of have a parallel processing going on with the quantum computer corresponding to the Hilbert space of, say, 2 to the n. Huge, huge things. What experimental demonstration do we have that this makes sense at all? Okay, we assume it's going to work, but in fact, there's not much actual demonstration that nature allows us. We totally expect it, and we totally expect it to be broken by dirt physics like decoherence. But if we can do an experiment, let's do that. And I would say it's not just making a lot of qubits. Your Hilbert space, if you make n qubits, if you make 51 qubits, your Hilbert space is not 2 to the 51. You don't know that. You have to do careful measurements. And to understand that, you have to understand quantum complexity, which is a whole nother conference and crowd of people. So doing that. Now, the basic idea by Preskill, it's a very nice definition, just say it shortly, for a well-defined problem, show more computation power for a quantum computer. That's what we want to do. And we're basically going to do an experiment where we can take a few seconds worth of data, and to check whether that data makes sense, we're going to have to run a classical supercomputer, maybe for a day, okay, to be able to check that, okay? So that's the basic idea. So it's powerful. As I said here, it's really nice because we can do fidelity. We need lower errors in qubit control, use the validate control. This is a way to make sure we can do it. And kind of what you need to do for supremacy is what you need to do for error correction. So it's a good milestone. And then I'm also going to say we plan to do it in a universal manner so that it's forward compatible to a general purpose quantum computer and doing error correction. But I would say the last thing here is, as a manager, I want to motivate my group to do 2 things. It's both to make really well-controlled, good coherence qubits and to scale it up, and to do that in a balanced way, doing that at the same time. And this is actually kind of a nice way to do that. Okay, it's a very simple algorithm. You just make a general quantum circuit, start in the ground state. You have some single qubit gates, which are Cliffords and non-Cliffords. It won't work if you don't have any non-Cliffords in there. And then some entangling gates, say a CZ. And you just do that over and over again. And these gates here are known but randomly chosen from that gate set. So you know what it is, but it's randomly chosen. And then you just run this, let's say 100,000 times, about a second. You'll get some outcomes here. And because this is some random circuit, okay, you really have no guess what's going on. So kind of classically, you just know that every state is going to show up there. 0, 0, 0, 1, 1, 0, 1, 1, et cetera. They're all going to be there. However, when you actually do the quantum calculation, some states are more likely than others due to what we call qubit speckle. And a nice way to kind of see this is that to look at the analogy, a very, very close analogy, in fact, between this qubit system and a laser pointer. This is a 0.3 watt illegal laser pointer bought in China, okay, and they stole my credit card number, so it's good karma. And then I have a piece of frosted glass here taped on to make it safe, and I got this through the airport screening in Europe, so you know, this is good. So we look at the output of this, and okay, so this is not going to show up at all because there's too much light. So what you see here is the light coming out, diffracting across, and what you see is speckle. Okay, in some directions the light is bright, in some directions the light is dim, because as the laser light goes through, sometimes they coherently add and sometimes they coherently subtract. And some directions are brighter than others, and the qubit analogy is that some outcomes probability will be higher and some will be lower. Okay? So you can calculate what that is, and this is what's hard, and you store that in a lookup table. Okay, and this may take days and lots of memory storage to do that. And then you do a correlation. You want to see is if the things you measured, the states you measured, which are the bright ones, did they have higher probability? And the way you do that is just do this cross entropy, where you measure K, but you use, for that value of K, the computed P, and if this is brighter, this is going to be bigger, it's going to be bigger than P classical, and that number is going to be bigger than 1. Okay, and you do the proper thing, and it's quantum, it's 0.42 for the cross entropy, and if it's totally random, white light, it's 0.58. There's a difference of 1 between the two here. And you just, sample the things and see if this is right after doing all this. So like I say, it takes lots of time with this. It takes a fraction of a second to take the data. You check it. You do it again and again until you run out of money doing your computation, and you claim everything's good. So the speckle tells you there's coherence. And if you can predict the direction of the light, it tells you whether you have good fidelity. So there's kind of two elements to this that's useful. Now, to understand in detail how this works, what you do is you look at, for example, the real and imaginary part of the wave function, and that's going to be Gaussian distributed because of the random nature of the problem. And if it's randomly distributed in a real and imaginary, but the amplitude is the radius, probability is that squared, then you're going to get a distribution that turns out to be called Porter-Thomas, but it's exponential distribution. So this is some numerical data, probability normalized to the classical probability. You see lots of low probabilities, a bunch of high probabilities. And in fact, if you take this and just sort it from low to high, okay, then what you see is this nice exponential curve, again, just saying that it's Porter-Thomas. Now, what's really useful is that if you take this exponential distribution and then look at it, if you have one random error in your circuit, and X, place anywhere, a bit flip or a phase flip, anywhere, 1, it then goes to a flat kind of non-speckle white distribution, okay? And with that very simple observation, then you can compute S total for a real circuit. And you just average the quantum and classical with no error in error. And you just include all the errors of 1, 2 in measurement, and it's basically E to the minus number of errors. Very, very simple calculation. Okay? So exponential decay. You need, to be out here where it's not classical, you need the number of errors less than order 1, maybe 2 or 3, something like that. Okay, and then what's nice is you can just measure the cross entropy, and then you know the number of errors very accurately. And then you can figure out the fidelity of your system. So this is really cool. Very simple measurement. So does this create a train wreck? Can we do this? Take 49 qubits. You need a 7x7 array. Okay, so that you'll completely entangle them in at least 7, maybe a few more operations. But right now we have about 0.5% errors for our Xmon qubits, and the number of errors is about 2. Okay, so maybe we have to do this better. I presume we do, and numbers indicate we have to do maybe about a factor of 2 better. But it's kind of within range of what we can do, and certainly we can use this for testing. Okay. So let's talk about the experiment we did to test this. Okay, it's a quantum supremacy algorithm. We haven't shown quantum supremacy with what we got, a superconducting qubit called a Gmon, which are kind of what we've seen before. These are islands of the capacitance. But now what happens is between the qubits, we have what is essentially mutual inductances between the two loops here. And this current here basically changes a Josephson junction, so we can change the mutual inductance between a positive coupling to a 0 coupling and to a minus coupling. Okay, so we can electrically tune that. And what that allows us to do is change the swapping interaction between two qubits, okay, with this electrical tuning here on kind of 1 nanosecond timescales. Okay, and the magnitude of that is maybe plus or minus 30 megahertz or so. We can also do single qubit control, full qubit control, as you normally can. And we do that with these 2 wires here with about 100 megahertz of control, or maybe a little bit more for Z. And thus we can write the full Hamiltonian of the system doing this, okay? So that we can do things in nanoseconds. The coherence time is about 20 microseconds, so we have a long time to do some kind of simple algorithm. But what's amazing is that we can calibrate all of this to about 0.1 megahertz or about a part in 1,000. And we can calibrate this very accurately, okay? And I want to say there's something really kind of amazing going on here. We're going to calibrate this qubit and this qubit getting coupled with just doing, calibrating that one coupler at a time. And then we're going to do this one, and then we're going to do this one, and we're going to do that one, and we calibrate it. But when we run our algorithm, we're going to turn all the couplers on and off at the same time. Now, that's not how we're calibrating it. And the question is this going to work at all? Can we predict what's going to happen here, even though we're running it in the way we didn't calibrate it? And I'm going to say, just ask the question, how in the heck would you go about validating whether this was correct? Okay? Whether, you can turn all 9 of them on and off and get it to work. It's not so obvious how to do that. And this is what's great about supremacy experiment, the quantum supremacy experiment, because it gives us a way to figure out how to do that. This one. So this is the algorithm, how we're going to test it. Okay? So here's 5 qubits. We're going to do a pi pulse on 1 and 3 to put a 1, 0, 1, 0, 0 state. We're then going to move them to different frequencies, okay, which are randomly chosen but known. And then we're going to turn on all the interactions at the same time. We're going to turn them on and off, okay? And on average, they're going to be about 25 nanoseconds, which for 2 of them is more or less an I-swap gate, okay? But we're going to do all of them at the same time, and then we're going to have a randomness that sometimes we're under-swapping and sometimes we're over-swapping, okay? And this is known and calculated, and this basically gives you a bunch of unitaries that changes this state, and then at the end we're going to measure it. Given that this is photon conserving, we're going to only look at the states which are 2 photons, which are most of the states. So we're going to post-select, but it doesn't really change much at all. But clearly that's what you want to do given this. Okay, so that's the experiment. So here's 5 qubits. Here's some instance 1. And we see the Porter-Thomas distribution, exponential, a lot of low states, a few high. We changed the way that we're doing everything. It's known, but we changed it. And again, some are high, lots are low, same thing here, okay? And this kind of distribution looks very speckly. So you automatically see that okay, it looks like things are coherent, but okay, you want to check it for sure. So the way to check it, is just to look for the exponential distribution. Okay, so you just take these probabilities and histogram them for all the different instances. So you can do that, and that's here, and I've normalized them by the number of states. For 5 qubits, it's 10, and 9 qubits and 126. You normalize that, and you get all the data falling on a very nice e to the minus x distribution, as you expect for Porter-Thomas. Okay, so it collapses to that. So that makes sense. Note that it's a little bit off here, and you might want to wonder what's going on there. The way to kind of understand that is to do the experiment where instead of, this was 5 cycles, we do 100 cycles, and now the distribution is this nice little Gaussian centered on the uniform distribution. And that's just the classical distribution where you have uniform light and no speckle at all. And it's not quite perfect, but it's pretty close to that. Okay, so you can kind of see that's what's going on. Decoherence kills the qubit speckle. And you can look at that. How much is the distance? It is from exponential distance, some measure. With 0 interactions, it's very far because it's not interacted and entangled. However, at 1, it's pretty good, and at 2, by the time you get to 2, which is only 90 seconds, but they're all interacting at the same time in this complicated way, it's pretty good. And then it gets worse over time, and worse as you get to increase the number of qubits, simply because of decoherence in the way that I showed you there. So you can make sense of that. Okay, we want to compare the probabilities. What I have here is the model predictions in red dots. You see where the measured probabilities are low, the predictions are low, and where the measured probabilities high, the predictions are high. This instance, this instance, this instance, this instance. So the speckle pattern matches what you expect from theory. And you can go ahead and kind of use the cross entropy. And here 0 is a random guess and 1 is a perfect prediction. So for 5 qubits, we get fidelities that are really quite good, okay, in the 95 down to 80% range given the number of cycles, okay? And again, this cross entropy gives you a direct measurement of fidelity. Okay, so it gets worse as the more number of cycles in a linear way. So your kind of probability way of thinking of these errors isn't so bad, okay? And then let's go from 3 to 9 qubits. And again, as you go to more qubits, the slope gets bigger. Again, in a way you kind of expect where the it's just you add the probabilities, okay? And you can look at 2.9% fidelity loss for a 9-qubit gate. That's really pretty good. Per gate and per cycle is about 0.3%, okay? That's really good. That's including control errors, not just bare decoherence, right? Whether we got this thing figured out and calibrated right. Now, 0.3% is a little bit better than what we've done before on the XMON devices, which are, let's say, 0.5, 0.7%. And of course, that's because we've neglected T1 decay. And here, T1 is about equal to T2 or so. So, you know, doubling this 0.3% to 0.6% or so for T1 decays kind of makes sense. That's fine. But it shows that, you know, we can really do very good control of this. Now, okay, the obvious question is, can we do a supremacy experiment? We just take these slopes and everything and extrapolate the 45 qubits, which, okay, it may not work. Okay, things can go wrong. I understand that. But as a minimum, you then would get this. And you see for a small number of cycles, you should be able to do that. And you have some margin here, too. Things can go wrong. So this, you know, we're very excited. We need to keep forging ahead to see if we can do things. You can use quantum supremacy to tune up your qubits. It turns out we have some flux biases, which we calibrate, but they're a little bit drifty in time. So what we do is we use the quantum supremacy measure, which is right here, just to do a Nelder-Mead optimization on the DC offsets of all these things. And this is very automatic. You don't have to think at all. You just plug it in and do it. And then it initially gets a little worse, and then it figures out which way to go. And you see by the end, you've made a significant improvement from here to here. And just to prove that this is not just, you know, you're faking this, what you do is you take half your data, half is used for training, half is a completely different data set you use for verification. The fact that these two track each other and the final answer comes out right tells you that you've verified your training and everything's okay. So this is great. We can use that to make better qubits or make better control, which of course is what we want to do. So I want to now talk about something we can do that's kind of interesting and fun, and it's still a toy problem, but it's still a bit useful. And especially if we want to start thinking about doing quantum chemistry or quantum materials problem. Okay, what can you do when you have a system that's really well controlled and have low errors, okay? And we're going to map to the problem called the Hofstadter butterfly, which you can think of as a two-dimensional sheet, for example, a graphene or some other material like that. And we want to know what are the energy levels of this system versus an applied magnetic field. And when you solve for that, here's the Hamiltonian. You basically have a fixed a coupling, a swapping between the sites, and then this cosine magnetic field dependence on the frequency, which you can see maps to our system. And you see this for 150 lattice sites. Very beautiful butterfly pattern here that repeats itself when B = 1, when one flux quantum is in this ring here, which for materials are about 10,000 Tesla, which is something you can't do in the lab. So it's kind of nice to see if you can do a simulation. So this is very interesting because of the fractal nature of this with large energy gaps and small energy gaps and really complicated spectrum over here. And what we want to do is see if we can understand that or see that in our quantum system. Now, for 9 qubits, it's not nearly so complex. So you calculate what this should be for 9 qubits. And you can, again, see this fractal nature where there's a big gap right here. And then in between the gaps, we have all this complicated structure having to do with that. OK, so that's the prediction of what the energy levels should look like versus this field. OK, so let's do the experiment. It's all calibrated. We plug it in. We do the experiment. We don't play around with it at all. We calibrate and run, as you would with a real quantum computer. So what's the chance you think we can get all this fine structure here and do that? There's a lot of complicated stuff going on there. So when we take the data, forget the energy levels, that's what we have. The dots are the experiment. And you see, they nicely fit on top of the lines, the theory. In fact, to see the difference, we've color-coded them. And the black lines are a few megahertz, and most of them are green, which is around 5 or 6 megahertz difference. And if you look at the scale, this is 300 megahertz here. So we are figuring out how to do this with a few percent imprecision, okay, just by plugging it in. And we see it follows all these little structures here, goes up and down really nicely. When there's a big collision, it tends not to be so good, but you can really get quite detailed information from doing that because the control has been calibrated well, and then we verified it and improved it with our techniques. So these metrics, these metrology experiments are super useful. Okay, so how did we do this? It's kind of cool physics. To measure the energy spectrum, this is single qubit excitation. You basically do a Ramsey fringe between one of the qubits, a pi over 2, where we change the phase of this to measure sigma x or sigma y. We get some complicated wiggling pattern versus time that we do the experiment, or time that this is on. And then what we do is sum these up and take the Fourier transform. And then you can see here that even though this is wiggling up and down in a complicated way, there's mostly 2 or a few more excitations. And if you do that for all the qubits, these are the tones that you get. It's like taking a bell and striking a bell, listening to tones. We strike it at different places to make sure we're exciting it in a fair way. You take all that average and you see 9 big peaks here. And these are the 9 peaks that I showed last thing. I just have to repeat it for all the different B fields. So it's a very nice way to do that. Now, given that you have all these energy levels, you can do a lot of physics to look at the energy level spacing and the statistics of that. So there's some measure of the energy level spacing. We can do that for both a small disorder in red and a big disorder in blue. And we see that the level separation uniformity defined in this way changes their structure from one to the other, corresponding to these 2 limits, with pretty good agreement to what we expect theoretically given here. So you can use this to very accurately look at the energy level separation physics and the localization physics. You can also do 2 photon spectroscopy. Okay, which is a little bit more complicated measurement. You now do Ramsey on 2 qubits, and you have to take this particular measurement operator sequence to do the Fourier transform. Again, this looks like a big mess, but you Fourier transform it and you get clear peaks. And then for all the possible 2 excitations, you get this little spectrograph of what's going on here, and you take the average of this and you get peaks that are now the 45 energy levels that you're looking for to describe the excitation energies of that. Okay? And then you can do some statistics on that, basically measuring their moments and showing versus energy or versus qubit lattice sites as you have more disorder, it gets brighter here in the center of the energy band or in the qubit lattice where this moment is bigger, basically showing that the disorder causes eigenstates to move to the center of the energy band or the center of the lattice. And again, this is something that's predicted by localization physics and something you can measure, quite accurately and do that. Okay, so let's see how many more minutes I have here. Okay, I'm good. Okay, now let's talk about where we're going here. Okay, so we've been working for 3 years to build up our scale-up infrastructure, and we're now kind of ready to show people what's going on here. So this is our latest 22-qubit chip in our chip mount, and this is basically the qubit chip here. There's 11 by 2 array of qubits right here, and then that is bump bonded with little 20-micron bump bonds here. You flip the chip over here to this chip, which brings out the wiring to the edge of the chip. So this is our special magic done at UCSB clean room. And then this is done by a foundry that allows us to get the wires out in a clean way. And when we bump bond that together, we place it in the middle here, and we wire bond the little connections going out to our microwave connectors. Okay, so this is 22 qubits. And using this technology, we're totally sure we can get up to the supremacy level by the end of the year. Now, there's something that's kind of magical that's happened here, which kind of disobeys the standard laws of experimental physics, where everything is always hard and you always find new problems. And what happened here is to get all these wiring to work here, we had to work really hard on just making sure that this was all done right. So to get all these wires out, we had to come up with that technology. But when we did this and started testing it, actually the control and coherence properties of the qubits got better too. So we were both able to scale and to get lambda better, or not, well, we haven't measured that yet, but to control it better at the same time. Okay, and this doesn't happen. So for example, when you put in Z pulses here to change the frequency of the qubits, when we first started this, we almost had unity crosstalk between one line and the nearest qubit controlling. It was really big. And then by fixing things, we got that down to about 0.5% in the 9-qubit devices that I showed you previously. Now in this chip, it is now unmeasurable. So that is about 90 dB isolation, really around less than 90 dB isolation, to the point I don't think we have to worry about it anymore. That's really good. The other thing before is we had microwave crosstalk, driving one qubit, the next neighbor we would see it, and it was kind of bad. And this one, we think right now it's about minus 40 dB or better. We have to do better measurements. But clearly things are better just because we're making the wiring and better. So I have a lot of optimism that with this technology, we can really improve a lot and go a long way and get this to work. Just as this is in the dilution refrigerator at 10 millikelvin, we run up a bunch of wires to room temperature here, just commercial coax. And then these come out the top of the refrigerator, and then we just have a bunch of cables that go to this crate here, which is our control electronics, which has been kind of miniaturized. And that particular crate, about this big, controls 22 qubits. Okay? So a supremacy experiment, it's maybe one rack. To go farther, we buy a lot of racks. And, you know, I was at Fermi Lab recently talking about this. And I kind of felt silly explaining to them they were going to buy a lot of racks to scale up because, you know, clearly people know how to do that. And then a big part of this, which isn't shown here, is all the computer scientists who are working on this to make it a scalable software, and in particular, to make it reliable software. Okay, no physics code allowed when we do that. So we work really hard on that, and that's a good thing about Google. Okay, so at that, I want to conclude, and let's see, what's the main point I want to get across here? I want to get across that measuring lambda is really useful, okay? And that's, in some sense, what I think of as a fault-tolerant threshold when lambda is bigger than 1. But to do that, we have to go from n equal 1 to n equal 2. You really can't measure that from an unerror-corrected qubit to an error-corrected. It's just comparing the wrong things. So let's measure lambda. Okay, that's what we're going to do with this next. And here we have our 22 qubit chips, and we expect to be able to make a, let's say, 7 by 7 array very shortly. That'll be done by the next end of the year. I'm sure we're going to get that. And then we'll be able to start testing it and start scaling this up. And hopefully we'll be doing some really good tests of quantum error correction very soon. So thank you very much.
Okay, we have time for a couple of questions, maybe.